Okay, I think it's time to get started. Welcome, everyone. Thanks for attending our special webinar today. It's part of a webinar series sponsored by Photonics Research, a gold open access journal jointly published by Chinese Laser Press and Optica Publishing Group. We launched this webinar series last year, hoping to take this as an opportunity to document the experience and the insightful advice from those greatest scientists who have made groundbreaking discoveries in the field of optics and photonics. And we'll run this in the format of a conversation through webinar interview. In addition to this live interview, we're going to publish the shortened version of the interview transcript later in the Photonics Research Journal. So I would like to encourage you to share this with others who might find this useful. And today, it's my great pleasure to introduce our guest honor, Professor John Bauer from the University of California, Santa Barbara in the United States. He's a world-renowned leader in the field of integrated photonics for optic communication. In addition to his career in academia, he's also a very successful entrepreneur. So as of now, he has founded many startups, including Terabit Technology, Calient Networks, Nexus Photonics, and some of them have been acquired. On top of all this accomplishment, he's also a great educator, giving advice and creating opportunities to many others. So far, more than 20 people from his group have become professors all around the world, and more than 20 have started their own company. And in addition to that, he also started the Center for Entrepreneurship and Engineering Management program at UCSB, which involved into the Department of Technology Management that offers master's degree, PhD, and certificates in technology management. He also founded a nonprofit, Unite to Light, to make a low-cost and healthier light source accessible to the world, specifically for those places with limited resources. So however, because of limited time, I wouldn't be able to finish the long list of his accomplishment. What I just mentioned is just the tip of the iceberg of what Professor John Bauer has accomplished. We hope to learn from his experience and hear his advice today. With that, I also wanted to introduce another important guest tonight, that is Professor Lin Chang. The interview tonight is a little bit special because it's a conversation between a mentor and his former mentee. Professor Lin Chang pursued a PhD under the supervision of Professor John Bauer. During that time, he focused on developing the strategies for advanced heterogeneous photonic integration to achieve new functions on integrated chips, silicon chips. And as far as I know, heard from industry, actually, people from the industry have started to adopt the strategy developed in their lab. That's really exciting. So in 2002, with all those achievements, Professor Lin Chang joined Peking University as assistant professor in the Department of Electronics. He is now a rising star in the field of integrated photonics. It's a great honor to have both of them. And also it's worth mentioning that our interview includes some questions that we collected during this registration process. Thank you to everyone who submitted questions for Professor John Bauer. There will be no additional question from the audience today. Now we'll start the live session. Let's welcome Professor John Bauer and Professor Lin Chang.
Yeah, thanks a lot, Professor Yang, for the introduction. So, hi, John. So I'm very excited today to have this conversation with you. So as you know, I spent 8 years in UCSB in our group. So under your guidance, I finished my PhD. And during that time, I have witnessed how a lot of technologies get developed and then finally change the world. So under your leadership and your great taste of the research, and the ability to commercialize things are the keys to make all those things happen. So for me, I have learned so many things from you. And I think the good thing is that through this event, and many researchers will also benefit a lot from your experience and also the stories behind your achievement. So let's start. And the first question actually is one I have always been curious about. So how did you become interested in silicon photonics?
Well, thank you, Lin. It was a great pleasure having you in the group, and you made so many accomplishments. I'm delighted to be here. Well, I got interested in silicon photonics because we were using silicon oxynitride waveguides to dramatically lower the loss of optical waveguides and open up new applications like optical gyroscopes on chips or optical memory. And this is exciting, but the prospect of integrating lasers, modulators, detectors with those waveguides open up a lot of new high volume, low cost applications like transceivers. And so the prospect of, skipping 5 or more generations of process technology and using modern packaging, to make scalable devices was very exciting.
Yeah, and you mentioned the integration of the laser. So, and now actually silicon photonics, as you mentioned, has nowadays become a very hot topic in both academia and industry. So could you talk about why it is so important now and how you vision silicon photonics transforming our world the years and the decades ahead?
Well, there's this very interesting convergence that's happening now between, electronics and photonics. And electronics is limited in getting data on and off the chip. And as communication speeds get higher and higher, copper interconnects are really not competitive. They take too much power, require too much equalization and regeneration. And so photonics has moved from simply being used for long distance communications to connections between racks and now chip to chip. And so the prospect of silicon photonics being used for every high capacity switching chip, every high speed GPU or TPU or processor, every high bandwidth memory is really exciting. And conversely, to make really advanced transceivers, we need electronics intimately integrated with it to lower the power required. So it's a very exciting time. And these photonic solutions to be integrated with electronics have to be on silicon, right? So you match the coefficient of thermal expansion of ICs and really take advantage of modern packaging, as exists for iPhones and things. So, no more gold boxes for photonics. I think silicon photonics will transform our world in the future because it opens up these high volume, low cost solutions. So not just transceivers and telecommunications, but healthcare, sensors, transportation, many applications that traditional photonics couldn't address because they were just too expensive.
Yeah, sounds great. So as everyone knows, your work in 2016 on successfully bonding 3.5 onto silicon waveguide has been widely accepted as one of the milestones in silicon photonics. It's also the start of the integration of laser on silicon photonics. Could you share some stories behind this work? So what kind of challenges have you overcome to achieve that?
Well, we had developed bonding for different materials to enable high brightness LEDs, work Rajiv Ram, now a professor at MIT, did, and for high performance VCSELs at telecom wavelengths. So this was successful. So I was pretty, convinced that we could use bonding to get 3.5 materials on silicon, and without the degradation and performance problems you get with epitaxially growing materials or anything with defects in it. So, the challenge, of course, is that 3.5 materials are not in silicon foundries, and there's a lot of concern about that. But they're all dopants, and as long as we exist on the copper side of it, I think it works quite well.
Yeah. So, and why you think a laser integration on silicon is so important? And could you talk about the impact of heterogeneous laser integration on silicon photonics?
Well, we all learned about the importance of gain when, fiber optic networks were transformed by EDFAs, right? And you could make much bigger, much more complex, and much cheaper networks by having gain in this optical network. And same thing was obviously true for electronics, right? Without gain, you really couldn't make an interesting IC. And so while many people around the world focused on silicon germanium for gain regions, it was really clear to me that indirect band gaps would never be competitive. They just wouldn't be as efficient as you'd get with indium phosphide or gallium arsenide technology. So to integrate lasers and silicon photonics would require direct band gap material. And, we originally called it, hybrid integration, the first work, but now more properly heterogeneous integration of, say, indium gallium arsenide phosphide and silicon. And again, it's just, gain regions with a lot of defects in it don't typically have good performance, high efficiency or high reliability. So by bonding materials that we grew on, pristine materials on epitaxial wafers, allowed us to get into these large wafer sizes, much larger than gallium arsenide or indium phosphide could do by themselves.
So as the technology gets developed, do you think now the heterogeneous silicon 3.5 laser reached commercial viability?
Yeah, it has. I mean, Intel has certainly led that, and they're doing, millions of transceivers a year. And, Juniper now OpenWave has pursued that. So, I think it really has it solves a lot of problems. So if you look at Infinera, a very successful photonic integrated circuit company, they typically have 5 or 6 epitaxial growth steps to make lasers, modulators, detectors, and or integrating contacts with waveguides. So those 5 or 6 regrowth steps is it's costly and yield limiting. But with heterogeneous integration, we can bond all the material at one time and process it all together. And so that's a real advantage. And so plus we can get much wider gain widths, right? You can go combine visible devices with infrared, with far infrared devices, all in the same PIC. So I think heterogeneous is really solves a lot of commercial problems for needed for high volume, low cost applications.
Yeah, sounds great. And actually, after the initial work, so you continue to lead our group and made many other breakthroughs in silicon photonics. Could you talk about several important ones?
Well, probably the most important one is the one that we did together, right? That you really led, namely making initially highly confined waveguides in lithium niobate for second harmonic generation, and then moving on to gallium arsenide. And again, the fact that you have a strong confinement makes the lithium niobate devices work better than on native substrate. And same thing, when you put gallium arsenide on top of silicon with SiO2 all around, then you get very efficient second harmonic generation, very efficient comb generation, much better than you would get on a native substrate. So heterogeneous on silicon, works better than on gallium arsenide or on lithium niobate. And so I think it's very exciting. Once we integrate lasers with these, devices, nonlinear devices, low loss devices, then you get, interesting comb sources. You can get very narrow line with lasers, right? Lorentzian line widths of less than 1/10 of a hertz already, and I think we can get to 1 millihertz. And so again, combining the very low loss of what you can get with waveguides on silicon with now gain or nonlinear devices makes much better devices. We started trying to make lasers that were as good on silicon as native substrate, but now we can make better lasers on silicon than native substrate. We always think of semiconductor lasers as being noisy, much worse than a gas or solid state laser, but now they could be lower noise, and that'll open up a lot of new applications.
Yeah, indeed. So actually, you mentioned that the hybrid integration in one of the previous questions, and as you know, there have been several different integration strategies. So what is your vision of different integration strategy, like monolithic, hybrid, and heterogeneous integration for the future of silicon photonic systems?
Well, certainly most people use, hybrid integration. The lasers may be fiber coupled to the PIC, or they may be adjacent to each other, and indeed that works well. So for, again, making narrow line with lasers, that works very well, but it's not a very scalable, high volume approach. On the other hand, when you go to heterogeneous, when you bond 3.5 materials onto there, you can do all this processing in parallel, right? All the laser integration and laser modulator detector integration all happens, processed at one time. The contacts are made at one time. And then you get all the advantages of, wafer scale testing, right? And I think that's really key for scalable, low cost systems. Eventually, I think monolithic will become important. So far, you give up performance and you give up reliability, but it's moving very quickly. So recently, we have been working on epitaxially growing quantum dot lasers on 300 millimeter wafers, and it works quite well. We can get, over 100 milliwatts output and pretty good reliability, but not as advanced yet as heterogeneous integration is.
Yeah. So actually, you have mentioned that there have been a lot of progress in the area of integrated narrow linewidth laser. And why are narrow linewidth lasers very important for silicon photonics?
Well, the obvious applications are certainly, coherent communications, particularly as we make, higher levels of, QAM and in general, optical gyroscopes need narrow linewidth lasers, spectroscopy needs narrow linewidth lasers. But in general, it's, linewidth is sort of a metric for lower frequency or phase noise, right? And so, what we've seen by integrating DFB lasers with, resonators is that the frequency noise and phase noise comes down by literally 70 dB or more. And so that has a lot of advantages for a variety of sensors, certainly spectroscopic devices, and others. So, microwave photonics works much better by pushing down that noise. And so I think it's really important.
Yeah. Yeah, you have also mentioned that the microcombs. So as we know that the microcombs over the last few years has become a very hot topic. And you are certainly one of the leaders in this direction. And what do you think that microcombs can bring to silicon photonics?
Well, the first is certainly just as a comb source, right? So by having, literally hundreds or 1,000 wavelengths that are very precisely spaced from each other, I think is really, important. I think you can do things like dual comb spectroscopy by having two combs that are slightly different in repetition rate. Opens, it's much better than traditional spectroscopic measurement systems, and so they can be compact, low cost, and I think we'll find a lot of applications. So yeah, it's a really exciting area.
Yeah. So maybe you can talk about a little bit about our recent demonstration of the optical frequency synthesizer and atomic clock by using the silicon photonics. So do you think in the future we can integrate the entire such kind of system on chip?
Sure. Again, most optical systems today use one laser or a couple of lasers. In that case, there's, you have different options. But the point of that paper was, by using a comb source with tens or hundreds of, tightly controlled wavelengths, combined with really fairly complex silicon photonic picks, allows us to demonstrate, very high capacity communications, 2 terabits in the case of the Nature paper, or also very complex microwave photonics, which was also there. So, Lin, you led that effort and made it successful. I'm glad I was able to support it.
Yeah, thanks. So, and also there have been recently another work paper just published in Nature, which is in the collaboration with Nexus. And this paper also overcome a long-standing bottleneck of silicon photonics. Could you talk about this work and how it will affect the silicon photonics in the future?
Sure. Most silicon photonic works use silicon waveguides and obviously all the datacom and telecom work at 1.3 and 1.5 micron. But obviously silicon is absorbing as you get into the visible region. And so the Nature paper with Nexus was about, silicon nitride waveguides and integrating shorter wavelength gain regions. So again, I think what we've done is just the beginning. And now, with Nexus pushing, 980 and 870 micron wavelengths, and then shorter wavelengths in the future, it opens up a lot of new applications. And it's essential then to have gain coupled to nitride waveguides, not silicon waveguides. And in a sense, it's a much harder problem, right? Because, 3.5 and silicon indices are about the same in index. So coupling between them is fairly easy. But, silicon nitride waveguide, particularly a thin nitride, where most of the energy is in the oxide, which is how you get the lowest loss, is, index of 1.5. So coupling from this 3.5 index to a 1.5 index is a much harder problem. But as that paper showed, you can get very efficient coupling, less than a dB loss, and very low reflection from those interfaces. So for the tunable lasers that were demonstrated there, that's absolutely key to get smooth tuning not to have reflections at those interfaces. And the really exciting thing about that paper, was the lasers lased up to CW, up to 185 degrees C, and so that's again allows us to now make tunable lasers that are not limited to room temperature operation, but don't need temperature cooling, and with wavelength measurement on chip, you can again have this laser uncooled and for almost any application. So, once you have visible wavelengths, then there's a lot of applications for AR, VR, and for atomic clocks and a host of new important fields. So, yeah, I think that was an important paper.
Yeah, indeed. So actually, you have published very many works in top journals over the last few years. So could you talk about how has the publishing process benefited your career?
Well, there's a famous phrase, which is, not to keep your light under a bushel basket. So it is important to find prestigious places like Photonics Research that many people read to get the word out on what one has done. So I think I've published 8 papers in Photonics Research and have been highly cited. So I appreciate the widespread readership. A story I've told many students about publishing involves Herb Kromer, right? So who won the Nobel Prize at UCSB for inventing the double heterostructure laser. And the interesting part of it is that his original paper was rejected. So I always tell students, don't get too discouraged if your paper is rejected. It was, if you take Herb, he was good enough for a Nobel Prize. And so fortunately, he didn't give up easily, right? And that's a key thing, is to not give up easily, but have your own strong opinion about the importance of the research you're doing. And so fortunately, he did get it resubmitted, it was published, and he did submit a patent, which was issued. And so he got the recognition he deserved. But again, the people doing some of the lasers at the time, this is 1962, 63, were not aware of his work. And so it's unfortunate. He could have impacted the field a lot sooner if he had worked, in one of the groups that was in that area. But he was kind of, working, at a different company that didn't do some of the lasers. And so it's important to make sure people learn about your work. Don't keep your light under a bushel basket. So.
Yeah, indeed. That's also a very important lesson for me. And I will also teach this to my students too. So, yeah, besides your outstanding scientific achievement, you are also famous for your greatest success in technology transfer from academia to industry. Could you share your experience on how to commercialize technologies?
I don't know that I know how to do it. Many people do it much better than I do. But, if you can get a big company like Intel to take up your research and commercialize it, that's obviously the best outcome. And so, going and giving talks at companies and at conferences is really important. But many times you do good research and no one picks it up, right? And many cases it's only the person doing the inventing or the development, like the student or whoever. And then if no one picks it up, it'll get lost, right? It doesn't cross that valley of death. And then you have to start a company to get it commercialized. And so again, many times only the inventors see the value. And so I've been lucky to work with a lot of brilliant students who took the ideas they developed here and developed into companies. And fortunately, UC is very receptive to licensing the technology to inventors, and they've been very supportive to me. So, I've taken, I think, 3 leave of absence to look at starting companies. And so UC has been very supportive.
Yeah, great. And actually, besides those questions, there are also many questions we received from the audience. So I saw many of them are actually from the young researchers seek for advice for their career. So as everyone know, you are very great a supervisor, and actually they are as Professor Yang mentioned, there are many people from our group start their own companies and become very successful. So what advice do you have for the researchers in terms of launching startups in silicon photonics?
Well, I think, as Wayne Gretzky famously said, you should skate to where the puck is going, not to where it is now. So if you're going to start a company, you can't do something that's immediately applicable. You need to kind of leapfrog existing companies and technologies and make a breakthrough. And so, while you're building the company, everybody else is progressing. So make sure it is a breakthrough and then pursue it vigorously, right? I mean, great ideas are important, but you have to assume that other people have thought of it too. And so you have to move very quickly to implement it and do it tenaciously, right? You can't give up. There'll be a lot of, down moments. And so anticipate that and just pursue it very vigorously.
Yeah. And also there are more than 20 people from our group who finally become professors. So if you're a grad student today, so given today's support for R&D, so would you have opted for an academia or industry career?
Well, again, I've been lucky to do both, right? I started at Bell Laboratories and really learned a lot there and worked with a lot of great people. And I have been lucky to be at UCSB, and they've given me the chance to kind of cross the line. And like I said, take, I think, probably a total of about 4 years leave of absence. So, both directions are ways to change the world, and that's what's important. The choice of academia or university or a company really depends what you enjoy doing. I enjoy teaching. I get a lot of pleasure of seeing students become successful, and so I'm very proud of what you've accomplished, and I take pleasure in that. So an academic career works really well for me.
So in terms of academia, do you have any suggestion for people who want to pursue a faculty?
Well, I think one thing is certainly to do a good postdoc. In many cases, you can go directly from a PhD to a university, but it's difficult to get a really good academic position. You compete with a lot of other people, right? And so, a good postdoc, I think can help you get a better, position at a better university than you might otherwise get. But in general, just throughout life, just keep learning, right? So don't get stuck in a rut, basically. So if you stay and do a postdoc where you did your PhD, make sure it's on something, a little different and something you can learn from. So for me, I was a grad student working in, solid state physics in zinc oxide world, again on silicon, taking, piezoelectric materials and putting them on silicon. But as a postdoc, I was working in the fiber optic field. And so it was a big change for me. And I learned a lot. And that really gave me a leg up when I went to Bell Laboratories.
Yeah, indeed. So also another very interesting question is that in addition to being a great scientist, you are also actually a great bicycle riders and snow skiers. So I recall that you once across the whole US riding a bicycle. And how did you become interested in these hobbies and how to maintain work-life balance?
Well, in that case, I saw a movie about riding the Tour Divide, which goes from Canada down to Mexico along the Continental Divide, and so that got me interested in trying that. I think the point is that to sustain yourself over the long run, you have to remain healthy and not allow work to run you down or not let your health degrade. So, exercise is really important to maintaining, vitality. And when I was younger, I used to run and play soccer and tennis, but my knees are not in such good shape anymore. So biking is a way to stay in shape. I do remember when I was at Bell Labs with Tom Wood and others, we used to run at lunchtime every day. And we were coming back after that. There was about 10 of us. And our boss was kind of irritated that we were all off at lunchtime running. And they asked us where we ran. And Tom Wood was smart. He said, well, we only run as far as you can get to in an hour. So we don't, keep it during our lunch break. But yeah, whatever you choose is fine, I think.
Yeah, that's very interesting stories. So, and finally, do you have any other advice for the young researchers today?
Well, I think, find something you're passionate about and pursue it relentlessly, right? And become the very best at something, right? That's certainly the expectation for anyone when they get a PhD is by the time they graduate, they know more about that topic than anyone in the world. And so it takes hard work, and it takes, you have to expect that you're going to be frustrated and have a lot of, downturns, but just have the vision that what you're doing is the right thing, and, getting a PhD and, or pursuing a particular idea. So, change the world. You can work on something very broad, or it could be very narrow, but do something that will have an impact. And so sometimes when students ask about a topic, I'll say, okay, fine, maybe you're right that, this will work and it'll be successful, but is anybody going to care? And so make sure you choose something that really will impact the world. And, we all only have a limited amount of time on this planet. So, it's important to make the world a better place with the time we have.
Yeah, thanks, John. And really appreciate that you're sharing all those valuable experience and insights. So I'm sure that many people today will benefit from them, and also in the future. And thanks again for spending your time for this interview. I look forward to more exciting news of silicon photonics from our group in the future. So thanks, John.
Thank you. That was very nice. Thank you, Lin.
Yep.
Okay, great. We finished earlier. That's wonderful. Professor Bauer and Professor Chang, thanks a lot for being with us today. I really learned a lot from the conversation. There's a proverb, actually, I want to quote whenever I hear a great conversation, learn from someone. It says, it's something I learned when I was young. It says, a single conversation with a wise person is better than 10 years of study of books. Professor Bauer, actually seeing the dynamics between you and Lin, who had smiles all the time during this webinar interview. Now I know why there's so many people from your group having successful careers. They learned from a great mind. And that is why I feel very grateful that today we have chance, because webinar we have chance to learn from you, learn from you. As a well-accomplished scientist, your advice is insightful and useful for many of us. Thanks for sharing the experience with us. Also, okay, so we have some extra time. What I want to do is share some slides with you about Photonics Research, which sponsored this webinar. So Photonics Research is a kind of new journal compared with many other optical journals associated with optical publishing group. It's a special partner journal co-published by Chinese Laser Press and Optica Publishing Group. And currently the impact factor is 7.254. It's ranked 12 out of 102 journals in the category of optics. It published both fundamental research and applied research. Basically, we encourage papers in all kinds of subjects in photonics. And as a partner journal, we have certain advantages. For example, we can promote research in multiple different social media associated with both Chinese Laser Press and Optica. And it's a great pleasure to share with the broad audience about the recent progress in your group if you submit and publish your work in Photonics Research. In addition to those regular papers, each year we have some feature issues led by some researchers which has reputation in specific field. For example, we have feature issues on subject each year to keep the community up to date on subjects in fast-moving areas. For example, in 2021, we have feature issue on deep learning in photonics, and some papers attract a lot of attention from the community, which is reflected by the high citations. And also this year, And we have this feature issue about integrated photonics, which is subject just mentioned by Professor John Bauer and Professor Lin Chang. It's really a exciting topic happening in both academia and industry. And next year, we will have another feature issue coming out, which is underway on optical metamaterials, on fundamentals and applications. So we can have feature issue in two ways. One is solicited by the editors of Photonics Research, or we can get proposal from the community. So if you have some idea about some exciting topic that is of broad interest to the community, I would like to encourage you to submit a proposal, reach out to us, and would love to talk to you about feature issues related to your expertise. In addition to feature issue, I also wanted to mention something very interesting, that is Editor-in-Chief Choice Award, which is associated with 10,000 renminbi. The value of the money is by no means reflect the value of the work. The research discovery is invaluable. And if you ask me what is criteria to choose the papers that can get this award, it's very simple. It's all about quality, impact, and significance. And it doesn't matter where it comes from. Over the past years, we have seen recipients of this award from small group, big group, senior group, young group. And it can be a group focusing on theoretical research or application-driven research. And I would like to also encourage you to submit your best work to Photonics Research, and I wish you the best to be the recipient of the next Editor-in-Chief Choice Award. And in the end, I wanted to emphasize again to make Photonics Research a great journal. We count on authors because I do think the criteria to evaluate whether a journal is good or not is not about the impact factor. It's about the reputation in the heart of authors. If someone wanted to choose Photonics Research as a venue to publish and promote research, then I would say Photonics Research is a high impact and great journal. So I would like to encourage all of you to send your papers to Photonics Research, because as I mentioned, we do have a lot of ways to promote your research. And we also have a special review process. All the papers submitted to Photonics Research will go through two steps. When the paper was submitted to the journal, the editor-in-chief will sign the paper to some editors. We'll have internal editorial review. And based on the feedback, we make decision. And for those papers who passes this initial screening, then the paper will be assigned to specific editors who will look for external review for the papers. And through this rigorous progress, we really keep the quality of papers published in Photonics Research. If you have any ideas to improve our journal or have an idea about the next scientist we should interview, please feel free to send an email to us. Here's emails you can contact. And in the end, let me stop sharing. I wanted to thank you again for being with us today. We won't have a successful event without your participation. And Professor Bowers, Professor Lin, thanks for being with us tonight. I wish you all the best and look forward to meeting you in the future. And also in the end, I also wanted to wish everyone a great day.
Thank you.
Thank you.